Assalamu alaikum and adab, dear students. Today's lecture is about the technical aspects of a steel column, how we design a column, how we calculate its load carrying capacity and other parameters. So, column is essentially a structural member which is known as a compression member. Compression member because, see, this is a column. It supports the beams transfer their load onto the column transfers it to the footing and then to the subgrade. Now this beam supports many loads, its own loads, live load, dead load, etc. Then it transfers the load to the column here at the support where it is supported by the column. Now since this load is of compressive nature, that's why the column is known as a compression member. It receives the reaction from the beam and which is compressive in nature, hence column is classified as a compression member in a building. Now come to the section of a column. See, there are three dimensions in a column. We have one dimension B, another dimension D. These are the lateral transverse dimensions. This is the length of the column along the height of the building. Then there are three axes, X, Y and Z. Z axis is the longitudinal axis of the column. This is the longitudinal axis. Now column is, in structural terms, column is defined as a structural member in a building in which load acts parallel to the longitudinal axis. See, this is the position of load. So this load is acting at the centroid. It is acting parallel to the longitudinal axis in case it is an axial column. In case it is a biaxial or a uniaxial column, the load may act on one of the axes or it may act somewhere here out of both the axes. But it has essentially to be parallel to the longitudinal axis of the beam. So a column, we summarize, a column is a member in which the load acts parallel to the longitudinal axis, and column is a compression member which will receive the load, which will receive the reaction from the beam and then transfer it to the footing below. Now we see the structurals. What structural members we normally use to act as a column? The most common type is an I section. Most common type, we normally use joist sections or beam sections to act as a column. Then as per the need, we can strengthen its flanges with the help of a flange plate. If the area required to be provided is more, if the load to be resisted is more, we can strengthen this member of single joist section by flange plates also. In case the loads are very heavy, then we may use two I sections together. We may combine two joist sections, then provide connecting plates, and this can be used as a column. Or else we may use channel sections also. Say a single channel section, this can be used as a column. It can be strengthened with the help of flange plates also. Again, if the load is heavy, we may use a combination of channels. We may place two channels and then connect them with flange plates at the top and bottom. So a combination of such members, this will be a single member if it is used as a single member. If we are using two or more members, then it becomes a built-up section. This is called a built-up section where we are using more structurals to combine them together to act as a column. This is as per our requirement, as per the need, as per the load acting over the column. Then we come to some technical part of the column, technical features of the column. Say we have one parameter, what we call effective length. Effective length of column, which is represented by small l. Now this column basically is slender type of a member in which the lateral dimensions are quite less as compared to the longitudinal dimension. this B and D are respectively less, or if it is a structural member, then the flange width of the flange, the depth of the member, these are quite less as compared to the length of the member. So this makes the member, the column, slender. Now in effective length, the total length of the column, this is the total length of the column L. Effective length is basically the length between two zero bending moment points. Zero bending moment points. So we'll have to locate the points of contraflexion. We have to locate the zero bending moment points along the length of the column. The distance between two zero bending moment points is denoted as the effective length of column. Say this is the column, this is the total length of the column, capital L. Ends are restrained. There are certain end conditions. This effective length of the bending moment points will depend upon the end conditions. Now these end conditions may be that the ends are held in position. They are held in position, or they may not be held in position. They are restrained in rotation, or they may not be restrained in rotation. So we'll have to see ends, whether they are held in position or not, whether they are restrained in rotation or not. For example, if we have the position, they are held in position and they are restrained in rotation, then the bending moment will start, zero bending moment will start from some certain distance from the fixed end, and it will terminate somewhere here. This will be the bending moment diagram for the column, and the zero bending moment points, corresponding zero bending moment points will be these, and the length of the column, effective length, will be in between these 2 points. So these details depend upon the end conditions of the column, and all these details are provided in the IS code corresponding to the end conditions. We have effective length details given in table number 5.2. In IS 800 5.2 table number, we are having all the details. What effective length should we take? What is the recommended value of effective length corresponding to certain end conditions? Say for example, this case where these are held in position, both the ends, they are restrained in rotation, then effective length recommended by IS code is 0.65 times the total. So this table will give us all the details for various end conditions, and conditions corresponding to those we will find out the effective length of the column. This column, since it is a slender member, it has a tendency to buckle. It has a tendency to buckle. So the failure, mode of the failure, most prominent mode of the failure is buckling. Column, it is having a lot of length. This length parameter is quite high as compared to the cross-sectional dimensions. It has a tendency to bend, or it has a tendency to buckle. So it will bend something like this. This will be the maximum deflection. Because of this buckling, because of this bulging, tension and compression, tension takes place, tension at the surface of the column will evolve, and that ultimately will lead to the failure of the column. So this buckling is prominent mode of failure in a column, and hence there is a control over this particular value in terms of slenderness ratio. We have another property called slenderness ratio. This slenderness ratio is denoted by lambda, and this is equal to the effective length of the column divided by the minimum radius of gyration. Minimum radius of gyration. So this value in columns, in compression members, this shall not exceed 180. So there is a limitation that this value has to be limited to 180. This should not exceed, this ratio should not exceed 180, otherwise your member is likely to bulge more and hence cannot be used as a column. So this value will say we'll have to limit it to 180. Now coming back to the slenderness ratio, this L we know now, this L we have obtained from the table 5.2. R minimum is minimum radius of gyration. Okay, this minimum radius of gyration will have to go by the basics. If we go by the basics, this R minimum shall be equal to under root of minimum moment of inertia, I minimum, divided by the area of the member. This is the basic formula. I minimum divided by area under the root. Now, area we know, area of the member we can obtain from the steel table. If it is a single member, if we are using a single I section or a channel section as the column, R minimum, we have RXX values, we have RYY values available in the steel table. For an individual member, we have these values available in the steel table. We can check out which is the minimum value and then use it as R minimum. But in case we have a built-up member, say a single I section but with flange plates here, if there are flange plates, we are providing flange plates to this I section, say it right here. This is the I section and it is provided with two flange plates, one on each flange. So it becomes a built-up member. Now, this R minimum you cannot take directly from the steel table because it is only for a single section available there. Now this is the XX axis of the member. This is the YY axis of the built-up member. Okay. For this I section, IXX we can take from steel table. We can also take IYY from the steel table. Okay, for the I section. But for the built-up member now, we'll have to calculate. We'll have to see our target is I minimum. Why, I don't know whether it will be along x-axis or it will be along y-axis. So we calculate IXX for the built-up member now. This will be equal to IXX of this ISMB, ISHB, whatever it is, plus IXX of plates. Now we'll have to see whether parallel axis theorem will be applicable. Plates will have their own axis here. It will be transferred to this. There will be distance h. So we'll have to apply parallel axis theorem in case of x-axis. This will become IXX for the entire member or the built-up section. Then we go for IYY. This will be IYY of the section ISMB or ISHB, whatever is provided, plus IYY of plates. Now since the axis or y-axis coincides, centroidal y-axis coincides with the plates, there will be no parallel axis theorem here. It will only be dB cube by 12 for two plates. So we'll have to find out which is the minimum one that we'll use here. Area will be the entire area of the I section plus the plates when it is strengthened with the flange plates, and ultimately we'll get R minimum. So from R minimum, we'll find out the slenderness ratio. Lambda will be L upon R minimum. After obtaining lambda, after getting this value of lambda, we'll see whether it is less than 180. It should not in any case exceed 180. Then our section is okay. We can go ahead and calculate the load carrying capacity for that particular section. So effective length and R minimum. These are two important parameters which we'll have to look out for steel column. So first of all, when the section is given, we look for the effective length of that particular column depending upon the end conditions, and we find out the slenderness ratio for that particular column. Then we come to the load carrying capacity. Load carrying capacity of column. So how much load it will safely sustain, it will safely take, that we will have to denote. So for that we'll have to see the data given data for that particular column will be the section itself. The sectional details shall be provided, which section we are using as a column, whether it is a single section or a built-up section. We'll have to see the length, what is the overall length of the column floor to floor height or whatever length is given, that is the total length L. Then we'll have to see the end conditions. What end conditions are there for that particular case, whether the ends are rotating, whether they are allowed to rotate or they are not allowed to rotate, whether they are fully restrained in rotation or partially restrained in rotation, whether they are held in position or they are free. So these conditions will have to be noted, because we have to calculate the effective length from the IS code table pertaining to that particular condition. Then we calculate the effective length of column. So from table 5.2 we calculate L corresponding to the end conditions, some coefficient multiplied with the overall length of the column, so we get L. Okay, from the steel table we go to the steel table. From steel table we calculate, we find out the area of the column, of the member, of the section which has been used as a column. If it is a built up member, then we will find out the total area by adding the area of the single member or the single joist, place the plates, something, whatever is given as per the condition. We will find out the area. Then we will have to find out R minimum, that is RXX and RYY. If again it is a single section, we can directly find out R minimum. For comparing these two values, we will find out R minimum, or as explained, we will have to calculate R minimum corresponding to RXX and RYY, then which will further depend upon IXX and IYY. For a built up section, ultimately we will obtain R minimum. So we have area with us, we have R minimum, radius of gyration with us. Then in the fourth step, we calculate the slenderness ratio lambda. Lambda will be L upon R minimum. Now we have both the values. We have effective length with us. We have calculated R minimum. We will find out lambda and check that it has to be less than 180. This ratio shall not exceed 180. It can be at the most equal to 180. Okay. Then we have to ultimately find out the load carrying capacity. So the load carrying capacity, safe load it will carry of the column P shall be equal to, this load carrying capacity is stress into area. So we will have area of the column, that is the gross area we have already had from the steel table, or we have added up the members, area of the individual members, and ultimately got gross area, multiplied by the permissible stress in axial compression. So this sigma AC is permissible axial compressive stress. This sigma AC is available in IS code table 5.1. So this is available in table 5.1 of the IS code IS 800. So we'll see a glimpse of that table. That table appears to be something like this. Here it is lambda. We have already got the value of lambda with us. And here it is Fy, the yield stress of steel. It means has different values, 220, 230, 240, something like this. Okay. So lambda, it starts from 10, then it goes to 20, then 30, then 40, and so on. We have already got this value lambda with us. This lambda, we'll see how to interpolate it in between which two values does our value lie and what is the Fy. So corresponding to those values, we interpolate this sigma AC for our case. So we have got sigma AC, we have got area. So this multiplication of the two will give us the safe load carrying capacity of the column. Okay, then we see the design steps of the column. Design of a column. Now, if load is given and we have to design the column, then which steps to follow, how to design this column. First of all, again, we will have to analyze the data given. Now there will be no section provided to us, but will be provided with the load the column has to carry, the actual load which the column has to carry safely, plus the length of column. And conditions is important. End conditions of the column. What end conditions are there? Length of the column and the load which it has to resist. Yield stress Fy. This should also be known to us, or if it's not given, we can assume the value suitably. After this, first of all, again we come to the effective length. We'll find out the effective length of column from the end conditions given from table 5.2. We'll find out the effective length of this particular column for the given case. Then we'll have to look for a section, a trial section from the steel table. But for that, we should know the area of the column required. So before that area also, we should know the stress permissible. We don't have those values right now. We don't have slenderness ratio so that we can go to the table and find out the stress. So what we do, we assume. Initially, we assume this value of sigma AC. Normally from 80 to 110 Newton per mm square. We just make an assumption, we assume the value of sigma AC so that in the next step we can get the gross area required. Gross area required. Gross area of the column required shall be the load which we know divided by the sigma AC value what we have assumed now. So this will give us the requirement of area for that particular column so that we can select a section from the steel table and then analyze it for the load given. Now we have gross area required. We'll go to the steel table and select a trial section. We go to the steel table. From steel table, we select a trial section. We select a trial section so that we analyze this section and find out whether it can be used, it will suffice the conditions given. So initially we may see if our area requirement is sufficed by a single angle, a single eye section or a channel section, then it's okay. If requirement is more, then we may provide plates over it. So a trial section, say for example, I have this eye section as a trial section. Okay. Now this eye section will have properties from the steel table. I will find out the area. I will find out RXX. I will find out RYY. If section is not providing us the required area and we have to provide certain plates over it, if this is the case, then I will find out the area as the area of ISMB plus area of plates. RXX I will have to find out for the built up section. RYY I will have to find out for the built up section. And I will find out R minimum for the built up section then, corresponding to IXX or IYY, whichever is lower. After this, we will analyze this trial section for the load, how much load it will resist. So before that, we'll find out slenderness ratio. Slenderness ratio for this particular section, either individual section or a built up section, lambda L upon R minimum. We'll check here, this lambda has to be less than 180 or at the most equal to this, it cannot exceed. So if it is okay, if this condition is sufficing, then we'll go back and find out the load this member can carry. So in the next step, we'll find out the load carrying capacity of the column as gross area multiplied by sigma AC. Sigma AC to be taken again from the table 5.1. I have now lambda with us. We'll interpolate this value and find out sigma AC by interpolation, depending upon the value of lambda and Fy yield stress of steel given. Then we go back and see what is the load carrying capacity of this particular section. This load has to be greater than or equal to the given load. If it is so, then our section is safe. If load carrying capacity is less than the load given, then the load given, we'll have to revise the section. Then its load carrying capacity is not sufficient, and we'll have to revise the section. We'll have to take a bigger section, a heavier section, and section which will have more area and hence give us more load carrying capacity, and revise the steps to find out another section. Ultimately, this condition has to be satisfied. So we summarize that a column is a compression member of a building which will be under compressive force. The member is a slender member, its length is more, cross-sectional dimensions are less, due to which it has a more tendency to buckle to failure by, it has a more tendency to fail by buckling. So there is a limitation for slenderness ratio, so that which buckling is kept under control, but slenderness ratio shall not exceed 180 in any case. Then we have effective length. Effective length depends upon the end conditions of the column, whether it is restrained, whether it is partially restrained, whether it is fully restrained or unrestrained, whether it is held in position or if it is free. So that values are given in the IS code. We can find out the effective length values. Then we have slenderness ratio, which will depend upon the effective length and the radius of gyration, minimum one. We'll have to see if we can get this value directly from the steel table if we have an individual section. If it is a built-up section, we'll have to calculate it from the basic formulas. Then we get lambda, that is the slenderness ratio. Slenderness ratio, corresponding to that, and yield stress, we have sigma AC, that is the permissible axial compressive stress values available in the steel in the IS code, and gross area multiplied by sigma AC will give us the load carrying capacity of the column. When we have to design on our own, we will first assume a value of sigma AC between 80 to 100, 110. This value of sigma AC to start up to select a trial section. Then we'll find out the area required, we'll find out effective length, gross area required. When we get, we'll go to the steel table, we'll select a section. Again, we'll see whether single section will suffice or we'll have to take a built-up one. We'll select a trial section which will give us area more than the required. That section, then we analyze, we again calculate the R minimum, then lambda. For that particular section, we analyze it for load carrying capacity and see whether it will suffice the conditions or not. If it is sufficing the conditions, if it is giving us a load which is more than the required one, then it's okay. It can be used as a column. If not, then we'll have to take another revision. We'll have to take another trial section until this condition is met. Thank you.